this video, we shall see deformation gradient and some numerical problems related to it, how to apply this deformation gradient. So we can say the deformation gradient is the center of heart of continuum mechanics. It is very important because it is used to separate the rigid body translations and rotations from the deformations. So we know during translations and rotations the body will not get deformed. So that clear differentiation will be there with help of this deformation gradient. We can do that. So these deformations are source of stresses. So when the body gets deformed, when the body is strained, then internal stresses are developed against that strain, which are known as stresses. The deformation gradient is involved in all equations relating to the quantities before deformation to corresponding quantities after deformation. So the same quantities, how they will be changing after deformation, those will be mapped with the help of this deformation gradient. Okay, the deformation tensor enables the relative spatial position of two neighboring particles after deformation to be described in terms of their relative material position before deformation. So the positions of the existing points in the spatial configuration after deformation can be explained with the help of existing material configuration before deformation. So here you can see two pictures, those are showing so for example, let us see this first picture. Okay, this is having coordinate systems capital X1, capital X2, capital X3, and you can see d capital X1, d capital X2 are the length of vectors here, q1 and q2. So q1 and q2 points from P. Okay, P is the point we are considering in this material configuration. So at a time t is equal to 0, no deformation at the originated state. Okay, there is no deformation, we can say it as a material configuration, okay, or undeformed configuration or reference configuration. And after deformation you can see how this circle is being deformed into this in this manner, and we are representing the points q1 and q2 with small letters here, lowercase letters, and p also the lowercase p here, dx1, d small x1, d small x2, all these are known as deformed in the deformed configuration, or we can say current configuration or spatial configuration. So both are three are same for this. uh, so for this I said, let me repeat, this is the material configuration or undeformed configuration or reference configuration. After deformation we can say this is the deformed configuration or current configuration or spatial configuration. And in spatial configuration we represent all the parameters in lowercase letters. In material configuration we represent the points in uh, capital letters or uppercase letters. So this is after time t, this is the deformation. Okay, so this is a picture. All these Cartesian coordinates in lowercase will indicate the spatial coordinates. uh, okay, consider two material particles q1 and q2 in the neighborhood of material p. So we are now concentrating on the point p and its surrounding part. Okay, so in that surrounding part we are taking two vectors, 2 points here, two more points q1 and q2 at the distances dx1 from p, dx2 from q. So this is also same after deformation. So it will be little deformed and all the parameters are same, but they are represented in lowercase letters. So now you can see the position of q1 and q2 relative to p are given by elemental vectors dx1 and dx2. So dx1 I can write it as now this xq1 minus xp, xq1 minus xp. So this minus this. So if you just uh, subtract this length xq1 from xp, you will get this dx1. Similarly dx2 is xq2 minus xp. So that let us take those equations as 1 and 2. So after deformation the material particles q1 and q2 have deformed to current spatial position. So it is given by mapping. So we are just mapping this. So with the help of mapping we are denoting this spatial coordinates. So xp, so how can we represent xp? So this is deformation function of capital xp comma t function of xp comma t. So that is the xp, the particle will depend on the material, the exact original position with respect to time, original position and time. These are this is the function, xp is the function, it is depending on xp and t. xq1 is also same, this is also function of capital xq1 comma t. Small xq2 can also be given with the help of mapping this function of capital xq2 comma t, deformation function. And the corresponding elemental vectors, or we can say this chi as transformation function chi, this is chi. Okay. And corresponding to elemental vectors we can say dx1. So as we have written here, in the same manner we are writing this here. Small dx1 is equal to small xq1 minus xp, just like this. Dx2 is equal to xq2 minus xp. So we can do in both manners. So if we substitute these equations 3 and 4 in equation 6, so dx1 is equal to, what will happen, in the place of xq1 I will substitute this, in the place of xp I will substitute this, and take it as equation number 8. So that is just a representation. And here also in the same manner, for dx2 we are substituting this xq2 value here, we'll get this, and xp value, which is this, substituted here, and take it as equation number 9. So by definition, the deformation gradient tensor f can be expressed as the derivative of each component of the deformed vector with respect to each component in the reference vector. So that is this is the one. So f is equal to delta del x, I mean del chi by del x. So that del chi, which is depending on capital X comma t, that is the reference sorry, that is the spatial coordinate. So we can also mention it as gradient x x of x comma t. So simply we can, sometimes we can represent d small x by dx. So with that we can write this the position, the or the length of vector in the reference current configuration can be explained with the help of deformation gradient in this manner. So after this is a deformation gradient. Okay, with the help, if you multiply with the deformation gradient, you will get the exact position of this vector. So in initial notation we can say this is dxi is equal to fi capital I dxi. So wherever we use the capital letters in indices, so that capital letter will indicate that is in reference configuration. Small letters or lowercase letters indicate they are in um, mid, spatial configuration. So we can write, let us rewrite it again. F x comma t will be equal to dou chi x comma t by dou x is equal to gradient x of x comma t. So in initial notation we can write in this manner. F I small small I capital I is equal to del chi I by del xi. Sorry, yeah, we can write it in this manner, or we can just simply write it as del x, del small x by del capital X. So in general, f has 9 components for all t, so it is 3 by 3 matrix in general, and it characterizes the motion of neighborhood point. So equation 12.12a, so this equation 12, so it clearly defines the linear transformation which generates the vector dx by action of second vector tensor on the vector dx. So this is like y is equal to mx, that is like linear, just like linear equation. So it has the linear uh, component. So being this as the deformation gradient, just like y is equal to mx, m represents the slope, so f represents here slope gradient here. Okay, hence this equations 12 and 12a. So that is what just I have shown, these two equations, initial notation and direct notation. They define the transformation rule. F is said to be a two-point tensor involving the points in two distinct configurations. So one index describes the spatial coordinate xi, other index describes the material coordinate x capital I. So in summary, we can say the material tangent vector map into spatial gradient of vectors via deformation gradient. We can simply say Fij is equal to del xi by del capital Xi, and that is equal to, that can be written in the tensor form and matrix form as del x1 by del capital X1, del small x1 by del capital X2, del small x1 by del capital X3, del small x2 by del capital X1, small x2 by del capital X3, and so on up to del small x3 by del capital X3. So this is how the deformation tensor will be in matrix form. So if we see this inverse deformation gradient, we can say that derivative of inverse motion chi inverse with respect to current position small x of a material point exists. We can write it as, so f inverse x small x comma t is equal to this chi del chi inverse small x comma t by del small x. So if we see, so all these are with respect to capital X, with respect to material description, and here with respect to spatial description we are about to mention this material description and this g. So this is also having this small grad capital x comma t, and here we are using capital G. So when we are going from push forward, that is nothing but material to spatial, then we can represent in this way. When we are coming back, or pull back operation, when we are coming from spatial to reference configuration, we have to indicate it with a small letter grad. Okay, in initial notation, f inverse a capital A small a. So initially what we have written, for a small a capital A we have written, so they will be swapping. So like this, so you just see this FII. So you can see how they are, and they will interchange the position capital and small letters. So when it is inverse, f inverse capital A small a, that is equal to del chi A inverse by del x a, or we can write it as I. So as we have been using I, we can write it as f inverse I, fi or f capital I small I inverse is equal to del chi I inverse by del xi. So here important points to note, in the motion can be expressed as x is equal to x of x comma t. In some textbooks it is mentioned like that. So we can write the deformation gradient simply f is equal to del x by del small x by del capital X. So this deformation gradient can also be expressed in initial notation according to the tensor rule. We can write as summation I capital I ranging from 1 to 3 f I capital I e I into capital E I. So this represents the material description and this represents the spatial description. Also f I is equal to del xi by del capital Xi. So where lowercase indices refer to the current or spatial Cartesian coordinates, and uppercase index refer to the initial Cartesian coordinate. So confining to the single elemental material vector dx, the corresponding vector dx in the spatial configuration, we can write it as dx is equal to f dx. F is equal to d small x by dx. So we are writing this in order to give the inverse of the uh, deformation gradient. So we can write f inverse as, so f inverse is there, they will interchange. So dx will come upwards and small dx will come downwards. So in initial notation we can write in this way, f inverse will be equal to summation capital I and small I ranging from 1 to 3 del capital Xi by del small x. Here, so they will also interchange. So this will also be interchanged ei into ei. So we can see some simple applications of deformation gradient for better understanding. So we shall see a problem now. Consider the uniform deformation gradient deformation given by mapping small x1 is equal to 1 by 4 into 18 plus 4 capital X1 plus 6 capital X2. So here you can see small x are regarding small x represent the spatial description, and here this represents the material description, capital letters. So small x2 is equal to 1 by 4 into 14 plus 6x2. So find the deformation gradient f and its inverse. So we have this x1 like this, x2 here. So we have this deformation gradient for 2 by, as a 2 by 2 matrix we can write it as, because it is a 2D, two dimensional problem. This is del x1 by del capital X1, del x1 by del capital X2, del x2 by del capital X1, del x2 by capital del x2. So now we have this x1 value, this x2 x2 this. So partial differentiation of x1 with respect to capital X1 we have this. So so 1 by 4 constant will be constant derivative is 0, and partial differentiation with respect to x1 will be 4x1 will be 4, and the 6x2 will be considered as constant when we are doing partial differentiation with respect to x1. So we will have 1 by 4 into 4 1. So similarly del x1 by del x2. So 1 by 4, now we have to derive with respect to x2. So then 4x1 will be constant 0, 18 will be constant 0, and here with respect to x2 we have 6x2 derivative as 6, so that will be 3 by 2. So and similarly here x2 can also be derived in a partial differentiation, can be expressed in partial differentiation in terms of this. So same manner we are applying here with respect to x1 with respect to x2. So we have this equation, this matrix. The deformation gradient is expressed in a matrix now. So we can find out inverse of deformation gradient. So for the 2 by 2 matrix or any square matrix, we have def inverse as adjacent f by det f. That is nothing but 1 by det f is nothing but AD minus BC. So if you remember the det, so that is 3 by 2 into 1 minus 0 into D minus B minus C A. That is adjoint of the matrix. So we have, however, this 2 by 3 into 3 by 2 minus 3 by 2 0 1. So now we can write it as, if we take 2 by 3 inside, we can write it as 1 minus 1 0 2 by 3. So that's over. So we have found f inverse and f. So let us have very interesting problem now. After finding out the inverse and inverse of deformation gradient and deformation gradient, we have to apply them, how they the coordinates are being mapped, how the coordinates are being mapped with respect to deformation gradient. Let us see the question now. For a two-dimensional problem, the deformation is given by the explicit equations. X1 is equal to 4 minus 2 capital X1 minus capital X2. X2 is equal to 2 plus 3 by 2 capital X1 minus half capital X2. Determine the matrix representation of the deformation gradient and its inverse, and study the deformation of the unit square with the region omega naught. Consider the material line, a line element A naught, and spatial line element B with unit length. Show how A naught deform and carry out the inverse operation with the B. For the component of A naught and B, take 1 by root 2 comma 1 by root 2 and 1 comma 0 respectively. So here we have to use this values for A naught and B component for components. So this is the figure they have given to us. So initially what they have given, so they have given a naught was given. So a naught is the unit vector, so magnitude is 1. That is in material configuration. In spatial configuration we have B, so B is also unit vector, so magnitude of B is 1, and this B is given as 1 comma 0 the component, and here A is given as, so 1 by root 2 comma 1 by root 2. These are the points. So how the A is the vectors, and here this is B 1 comma 0. Now we have to do the push forward operation, material to spatial description, how A naught is being changed to A with respect to the with the help of deformation gradient. And we need to also find out how this B, which is already given, is being transformed or pulling back into material configuration and becoming B naught with the help of this deformation gradient. F inverse we have to use for this transformation of B into B naught, and for this transformation A naught from A we need to use the deformation gradient. Okay, this is description of this deformation gradient of a unit square, showing the map. So this is a square, unit square, so map chi of material. So this is a mapping, push forward. So line element A naught into A, and the inverse map that represents how B is changing to B naught. Okay, so given these are the equations they have given in the problem. So x1 is equal to 4 minus 2 capital X1 minus x capital X2. X2 is 2 plus 3 by 2 capital X1 minus half capital X2. So we know that deformation gradient is this. Okay, so just like in the previous problem, if we do that, we can get all the components. So those we'll get the deformation gradient minus 2 minus 1 3 by 2 minus 1 by 2. If you find out inverse of deformation gradients, applying the previous problem, Same as previous problem, we will get the inverse of deformation gradient as this much, the components. So now the problem starts. That given deformation chi carries the unit vector a naught into its new position characterized by a. New position, when it is transferred to spatial description, it is represented by just a, small a. By means of f inverse expression, sorry, f expression, not f inverse, f expression, we can get on the given components of a naught, we can specify the deformed position of a naught. So a naught, they have given us the coordinates as 1 by root 2, 1 by root 2, and we have the deformation gradient as we have found, minus 2, minus 1, 3 by 2, minus 1 by 2, a square matrix, 2 by 2 square matrix, and we need this small a. So small a will be changing into this, yeah, will be changing into this one. So this is what the mapping is. So spatial description can be explained with the help of this deformation gradient and material description. So that a is equal to, this is f and this is a. So if you do multiplication, this with this, minus 2 into 1 by 2, minus 1 into 1 by 2, 1 by root 2, 3 by 2 into 1 by root 2, minus 1 by 2 into 1 by root 2. So if you simplify, you will get this. So that is, you will get 2 by 1 matrix. Ultimately these are the points. So we have to find out the magnitude of this vector a. So that is nothing but we will get root over. So if we have ax1 plus bx2, the magnitude will be root over a square plus b square. So as we have studied in our school level, so magnitude of the vector is under root this square by this square. So we will get root over 5, or we can say 5 power 1 by 2. So magnitude of this a is root 5. The inverse of deformation chi inverse carries the unit vector b into undeformed position. So it is pulling back, the characterized by b naught. So after pulling back into material configuration, that b will be expressed by b naught. By analogy with the above, using f inverse and given components b, we may specify the undeformed position of b as, so b naught can be expressed as f inverse b. So what we have here, a is equal to f into a naught. Here if you take b naught, so that is f inverse b, so that is pulling back, so f becomes f inverse. So we have already f inverse value and given the matrix b 1 comma 0. Now we can simply apply this multiplication. We get the value of b as minus 1 by 5 minus 3 by 5. So if we take out minus 1 by 5, we will get this. Magnitude of this vector b naught we can find out in this manner. Just we have done it for small vector a. So 1 by 5 square minus 3 by 5 square, we will get 2 by 5 root over 2 by 5. So we have to conclude, we have to, so here we have observed that during deformation the length of a naught increases. So initially a naught is given as 1. So unit magnitude is it is unit vector as it given, so magnitude is 1. So that magnitude increases from 1 to root over 5 as we have found here. While during the inverse map of inverse map chi inverse, the length of b decreases from 1 to under root 2 by 5, this one. So that you need to observe, and the figure shows these two values. So here we have this a, so initially this is 1 unit, and this is b naught, which is newly deformed, under root 2 by 5 is its magnitude, and this a naught when deformed, so the new value is under root 5, and this b naught which is existing, after pullback operation it becomes root over 2 by 5. So that is how the vectors are changing their lengths, the magnitudes. So we can find out by using this deformation gradient. Hope you got a little, and you can find out this lecture notes in the description below. You can click on the link to access these notes. Thanks for your time.